Welcome to week 4 of the course, where we will be discussing about the stress analysis in polymers. So, until previous week we are looking at coming up with differential equation to represent viscoelastic behavior of polymers. But in this week we will look at an alternative method where we can use integral equations to solve the response of viscoelastic materials. So, for this we will start with the Boltzman superposition principle in this video. So, we will start with the Boltzman superposition principle, and then we will also show you a Boltzman superposition integral which helps you to represent the polymer behavior in terms of an integral equation. And then with few examples we will show how to use the Boltzman superposition integral. So, here we are trying to formally introduce you to the superposition principle, but a few videos back we have already seen for a material to be elastic it should show both superposition and proportionality. So, there we said what a superposition is, but here we will emphasize it and define it much more formally so that we can use it to solve problems. Okay. So, before we get into the details, a very big difference between this approach and the earlier approach where we had these phenomenological models is, here we say the relaxation modulus and the creep compliance, these are sufficient to predict response to any input. What it means is, for us the material behavior is captured through these, either the relaxation modulus E of t or the creep compliance d of t. So, we do not make any assumption about if there are any springs or dampers or whether it is a Kelvin, Maxwell or a combination of those. We do not look into those details. Without those details we are only interested in the two quantities, either of these, either the relaxation modulus or the creep compliance. So, let us start with a very simple loading which is the unit step stress input. So, we could have also started with strain input, but let us look at stress input to start with. So, what we have is a stress input which can be represented something like this. So, stress variation with time. So, here we are representing with the Heaviside function h of t minus t1, which means that the step happens at time t1, and this step is of amplitude sigma naught. So, for an input like this the response is simply given in terms of this creep compliance d of t minus t1. So, the strain response is the creep compliance times the stress amplitude. This is simply strain response to unit step stress input. But now let us look at if there are two steps, meaning that we are looking at two step stress input. Let us show it pictorially first. So, with time the stress varies in two steps, first at time t1 and then at time t2. This is time t1 and this is time t2, and these steps are given as delta sigma 1 and delta sigma 2. So, then we can write the input stress sigma t is the summation of these two steps in the stress input. Once we write it in this form, it is now easy for us to write the strain response, because the strain response is simply the summation of the creep compliance from the first stress input plus creep compliance from the second stress input. This is possible because of this Boltzman superposition principle, which states that the strain response can be written as the sum of these two responses to the unit step stress inputs. So, once we have this strain written as a summation of these two responses, we can also write it in terms of a summation. Summation I going from 1 to 2, and this written in terms of t minus ti, where it could be t1 comma t2, and delta sigma 1 and sigma 2 are replaced with delta sigma I. So, what we have shown here is a formal definition to what a Boltzmann superposition principle means. It simply allows us to take the response from two individual step inputs and add them together to find the overall response. But we can generalize this for an arbitrary input. So, this I am just reproducing what we have looked at in the previous slide for the two step stress input. But now let us look at an arbitrary stress input. Arbitrary stress input meaning your stress can be varying in any arbitrary fashion, right. But can that be represented using these step inputs or not? The answer is yes, we can represent it with multiple steps. The only thing is these steps or the jumps should be small, the delta sigma should be small. If we do that, then we can write this input sigma of t as the summation from 1 to n being the number of steps, and these some small jumps we are talking about are delta sigma i's. But let us say if we have very large number of steps, each with very large number of steps meaning n tends to infinity, and we also say that these jumps approach 0, then this summation can be replaced with an integral form. How do we do that? So, we now write it in terms of integral going from 0 to t, we write it as 0 minus, meaning we also include 0 in the input. This Heaviside function or the step function h of t minus ti remains the same. The only difference is now we said this ti we are replacing using a temporary variable for time which is u, and then this delta sigma I we have replaced with d sigma, because now we are talking about a small differential. And lastly, if we multiply and divide by this du, then it takes this integral form. So, this integral form is representing our input, but now let us see what is the response to this input. We will first start with the summation form which we have earlier seen for the two step stress input. So, we see that the strain is simply the strain with the first input plus the strain in the second input, all given in terms of the creep compliance d and these steps delta sigma I. So, similar to the input, if we now realize that this n tends to infinity and delta sigma I tends to 0, then this should also be written in the integral form. So, now we have the response strain response given in the integral form from 0 negative to t in terms of the creep compliance t and the input stress sigma. So, one can if you notice carefully, this 0 minus can be replaced with minus infinity as well. This is another form of writing the same equation. So, the only thing we have done is we have replaced this 0 minus with minus infinity, because we are assuming that to the left of 0 time t equal to 0 there is no input. But let us say if there is a stress history and if you want to take care of it, it is better to write this integral in terms of minus infinity. Then we take care of all the stress history as well into this integral equation. So, these are the two important or two different ways to write the strain response for any arbitrary stress input. So, since we see that both of them are in the integral form, we now can call them as the Boltzmann superposition integral, or another name to that is Duhamel's integral. So, effectively what we are showing in this slide is we can replace all the differential equations we have seen until now or in week 3 with this integral form. So, once we have this integral form, we are good enough to solve for any arbitrary input. So, the input could be a straight line or a curve which we can express in terms of an expression. And these, as you can see, are written in terms of these creep compliance. So, in summary, what we have seen in previous slide is if we have a stress input, then we get these integrals. They are also called as creep integral forms because we have the creep compliance D. So, I am showing you both the integrals, one with 0 minus, meaning that we are only considering until time t equal to 0 and later, but one can as well write in terms of starting from minus infinity, meaning it will capture all the stress history as well. So, here we started with stress input, but now let us see what happens if we start with a strain input. So, if we start with a strain input, we can repeat the same process and then come up with stress response in terms of E. What is E here? It is the relaxation modulus. So, now we have this stress response in terms of the relaxation modulus and the rest of the equation remains the same. So, this is our strain input and this is our relaxation modulus. Okay. So, notice here again we are writing in terms of 0 minus, but this can as well be written in terms of minus infinity if there is any history included. So, effectively now we have shown if you have an input as stress, we use this creep integral form, and if we have a input in terms of the strain, we use this stress relaxation integral form which is written in terms of this relaxation modulus and the input strain. Now that we have shown you the integral forms both for stress input and the strain input, let us do a few examples to demonstrate how we can use these integrals. With an example, we will show how to apply the Boltzmann superposition principle. So, let us say this is example 1 where we have the stress input given as sigma naught h of t, meaning that this is a step input. So, for this the strain response can be written in terms of the Boltzmann integral. How do we write it as? 0 to t d of t minus u times d by du of sigma u d. This is the integral we have seen in the previous slide. Okay, we just need to substitute this stress into the integral. Before we do that, we will write the stress input in terms of u, which is sigma naught times h of u, and the first derivative of this should give you as sigma naught is a constant and the derivative of the first step function is the Dirac delta function. So, once I substitute that here, d of t minus u sigma naught times the Dirac delta function delta of u du. So, here we can pull a sigma naught out of the integral because it is a constant. That should leave us with d of t minus u times delta u du. Okay. Now, to solve this integral, I need to recall the convolution integral. This will be looking in the next week, but quickly I will show you the formula and use that to solve this problem. So, what it says is Laplace of this integral, let us say the integral is 0 to t, the first function is t minus u times the second function written in terms of g of u du this can be written as product of the two functions in the transform domain, which means f of s times g of s. Okay. So, here we will identify that we are writing the first function is this d and the second function g is the Dirac delta function delta of u. So, now I need to write what are the Laplace of this. So, let us say we are applying the Laplace on both sides of this equation. We will first write it as epsilon of s equals sigma naught times. What is the Laplace of d of t? It is d of s. And now, what is the Laplace of Dirac delta function? So, we can use this formula which says Laplace of Dirac delta of t minus a is given as e power minus as. But in our formula, what is the value of a? The value of a is 0. So, which means if I say the Dirac delta of t, Laplace will be simply 1 because a equal to 0 and e power 0 is 1. Okay. So, let us substitute that here, which means the product is 1. So, on both sides of the equation we only have one Laplace term. So, once we inverse Laplace transform, which means inverse Laplace on both sides, and here we have applied the Laplace on both. So, once I apply the inverse Laplace, I should get it as response strain response is simply epsilon naught times d of t, which is the solution to this problem. So, what we have shown is for this stress response we have used the Boltzman integral. For here we have used the Boltzman integral with d, which is the compliance, because the input is the stress sigma of u. And using this integral, and we have, once we invoke this convolute integral formula, then we are able to find the solution. So, here is the second example where we say the loading is a constant strain rate. So, the strain varies with time as a constant value, and that value is r. So, how do we represent that? We say it is epsilon of t is equal to r t times h of t. And then we will also say that we will assume that the material behaves as a Maxwell model. Okay. So, now we have seen that the input is in terms of strain. So, if the input is in terms of strain, which integral do we use? We use the stress relaxation integral written in terms of E of t minus . Okay. So, this is the stress relaxation integral for to find the stress response. Again, let us write the input in terms of u, so which should be r u, and then d by du of the input epsilon of u is simply r. So, now if we substitute this into the integral, we get it is 0 to t e of t minus u times r. R I can since r is a constant, I can take it out of the integral and write it as du. So, at this time we need to know what is this function E, which is the relaxation modulus. For this, it is given in this problem that it is a Maxwell model. So, for a Maxwell model, what is the relaxation modulus, it is given as E times e power minus t by relaxation time tau. But since in the integral form we have it as E of t minus u, now if we write this relaxation modulus, it should be E times e power, we will simply replace t with t minus u. So, it is minus of t minus u by tau. So, now let us substitute this into the integral. E I can pull out of the integral and it is simply e power minus t minus u by tau du. So, we know the integral for an exponential function, it is simply the exponential function divided by the coefficient. So, it is the coefficient for u is 1 by tau. So, which means it is written as R e tau evaluated within the limits of 0 to t. So, we will write it as e power minus, I can also take it inside, then it will be u minus t by tau evaluated at 0 to t. That should give us, when u is tau, it is e power 0, it is 1. So, R e tau 1 minus, when e is 0, it is simply e power minus t by tau. So, this should give the response, the stress response to constant strain input. So, earlier we have solved the same thing using differential equations, but here what we have done is using these Boltzman integrals we are able to get to the same answers. Okay. Now, let us extend this problem a little further. Now, let us say the kind of input is so let us say the strain is varying with time and let us say these times are T1, T2, T3, fine. So, for this kind of input, if we were to find what is the stress response, how do we find? So, earlier we have shown that we can use the superposition principle. So, once we say that we are using the superposition principle, then we should be able to write this input as, how do we write? So, the input is only starting at time t1 and there it is going at a slope of r and here it is coming down at a slope of minus r. So, this should be written as r t minus t1 This is the input when for the initial loading between times t1 and t2, but for times between t2 and t3 it is r of t minus t2. Since now the slope is coming down, it has to be minus 2r. Because if it is simply minus r, then that will remain as a constant, but since it has to come down, it has to be minus 2r. h of t minus t2 plus again at the end after t3 it has to remain constant. So, again it should be r times t minus t3 times h of t minus t3. So, for this one should be able to write the stress response in terms of the relaxation modulus. So, this is the expression for the times between T1 and T2, but if we are looking for the response between times T2 and T3, it should be the response from the first two inputs, which can be written as again this is applicable in the times between T2 and T3. And finally, for times above T3, it should be the sum of all the three inputs, which can be given as and this is applicable for times t greater than T3. So, we will have three expressions depending on we are looking at the response at what time. If we are looking at times between T1 and T2, we go with the first expression, but if we are looking for response between times T2 and T3, we go with the second expression. And finally, if we are looking at response beyond this time T3, then we go with the final response. So, in summary, in this video we have started with stress input. For a arbitrary stress input, we said we get this creep integral form written in terms of this creep compliance and the input stress. And if the input is strain, then we have this stress relaxation integral form written in terms of the relaxation modulus E and the input strain epsilon. So, bear in mind this d of t minus u and E of t minus u can be obtained by any means. One can do an experiment and give you the curve, or to make it simple you can say once you do the experiment you can fit it with standard models with the spring and dampers, which will help you to find these creep compliance of the relaxation modulus. So, the point I am trying to emphasize is the material behavior is captured with this creep compliance or the relaxation modulus, which are critical for us to evaluate these integrals. So, with this I will conclude this lecture.